Happy to speak here. I will talk about the CISS effect, the chiral-induced spin selectivity effect, but only on one application because the time is short, and I will talk about spintronics or spin electronics, which could be done. So this is my group, and we are a large group, and we are group working on the CISS effect, on which I will talk. We are working on quantum biology, on spintronics, and quantum sensors, and other superconductivity and other stuff. We are quite a large group. So what is the motivation of going even to spintronics? Spintronics is spin electronics, which means you use the electrons or the electron spins and not just the electron. And there are a lot of work in spintronics. And if you think about spintronics, is when you force an electron or you choose a spin, you are less immune to scattering and you want to work in higher frequencies in principle. It's like when you rotate a football, it's a rotating football, it's immune against scattering, and because you preserve angular momentum, so you have less scattering, so you can in principle go further to the thermodynamic limit. If you talk about memory devices, you want the memory to be stable at room temperature, so you want to be close to the thermodynamic limit, but not too much far, because there you invest a lot of energy when you're far from the thermodynamic limit. So in electronics, you are 2 orders of magnitude farther than the thermodynamic limit. In spintronics, you can get far closer. And in principle, you can get better energy in heat dissipation, and you can have much more efficient and faster energy scale. However, usually spintronics or spin electronics require a very complicated device structures. You need 2 magnetic layers. One is a hard magnet and 2 is a soft magnet. You need to switch one and not the other. And you need to do those 2 magnetic layers very close, very close to one another, while one is influencing the other. So the CISS effect, the effect I will talk about, can solve those problems, and I will explain why in this short seminar. So the CISS effect is a chiral-induced spin selectivity effect. It talks about chirality. Chiral is a hand, so you have either right hand or left hand, a chirality, and symmetry can be broken either to the right or to the left, like the 2 hands, and they cannot be superimposed one on top of the other. So you have a symmetry which is broken, and many molecules and material have this kind of symmetric or mirror-like symmetry, which they have like right and left hand. So if you talk about it, biology is chiral, which means a lot of proteins, DNA, amino acids, sugars are chiral in, they break the symmetry of right and left hand. What's interesting about biology is that it's a chiral, but only with one kind of chirality. Only one kind of, many proteins in biology have one kind of chirality, and this is preserved through all evolution. If you do chemistry, you will have both kind of chirality, usually unless you break the symmetry by forcing energy, but if you just take entropy, you will have only one, you have 2 kinds of chirality. Biology breaks the symmetry, and we were studying to see why this is happening and why it's preserved, and this is the effect I'm talking about. This is a chiral-induced spin selectivity effect, which means if you force a current to go through chiral potential or chiral structure, the current will become spin selective. Only one kind of electron spin will pass through this chiral potential. So if you have one chirality and we force the current to go upward, one kind of spin will go in that direction. If you force the current downwards, the opposite spin will go in that direction. If you have the opposite chirality, the opposite kind of spin will go in the up direction. And again, we switch direction if we go to the down direction. So this is an interaction between the electron spin and the chirality when it moves through the chiral molecule. Why it is happening? It is happening because the electron, when going through electric and magnetic field, and it is forced to go in a very small and very narrow potential, has a chiral root, and this chiral root is like having a very large effective magnetic field. And this huge effective magnetic field splits the spin, and only one spin can polarize and pass through the chiral molecule. So a chiral layer, a chiral molecule, a chiral filter can act as a very efficient spin filtering. And this is the reason why biology is chiral, because any charge that will start will have a circular polarization, will have only one spin, and it is stable against environmental changes, so it calls homeostasis. But for our case, for spintronics, is also things that you can use those layers is for achieving very simple spintronic devices. So if you want to have simple chiral spintronics, or simple memory, magnetic memory, we can use this effect, which we found from biology, and have a chiral layer, which is easily to reproduce, can have a very high spin polarization, much more than standard spintronic device, and it's very efficient and very simple. It can also be able to have a future magnetism, like when we use fermions, or which is dense magnetic, or use magnetic material which can have very dense memory, like anti-ferromagnet, where we can have very dense memory. This effect could talk to those two structures, So how this is done? So it's actually very simple. We can talk about optical memory, or we can talk about electrical memory. If you have an optical memory, we excite something, which could be a quantum dot or any something which excite, and you have charge oscillation through the chiral potential. But since we have one spin going in that direction and the opposite in that direction, we'll always have a spin torque or magnetization of the surface just by shining light on this chiral layer. And we can magnetize locally this chiral layer. In a magnetic device, it's even simpler. What we need to have is a magnetic plates, and we can magnetize it either up or down and inject current and see if the resistance is high or low. So what are we talking about? We are talking about memristors. We want to have embedded memory. This is called a memristor, a memory and a transistor. A memory and a transistor will have this kind of very strange IV curve. You want something which is nonlinear, and this is behaving like a transistor. You change the voltage and you have large change in current, but you want also a dual layer or a memory structure which will be 1 or 0, which means we'll have other hysteresis, 1 or 0, we'll have both kind of structure. This kind of devices like the missing device could act as embedded memory because it could do both logic and a memory kind of a device. So how could we do a device? This is a very simple device. This is a gold contact. This is a chiral layer, which acts as spin filter. And this is a barium ferrum oxide, which is a magnetized ferromagnet. It is done in ETH. It could be either magnetized in the up or in the down direction. And if we inject current, the current will be spin polarized. It will be either injecting in the direction of the magnetization, so we'll have high resistance, or in opposite direction, so we'll have low resistance. But we can build this kind of very simple device, bottom gold contact, ferromagnetic particles and chiral structures, and magnetize the magnetic particles either up, and then we'll have high resistance and low current, like the red curve, and this is voltage versus current, or low resistance and high current, like we have the blue curve, and we can have hysteresis by switching the magnetization. So this is exactly like a memristor using nanoparticles, with a two-level system, either the blue or the red. If we want to go even smaller, there are two major problems. First of all, the unit size should be reduced because usually magnetic memory is about 70 nanometers in size, and we want to go even smaller. And the second thing is we need to find an erasing mechanism, because here we erase by external magnetic field. We want the device to erase by itself. So this is what you can do. You can take two contacts, which are apart from each other by 10 nanometers. So this is done by e-beam lithography. And then you put chiral molecules on top. So this is a real device, and this is a drawing. You put chiral molecules on top, and so this acts as a chiral filter. And then you put the magnetic particle. So the magnetic particle is a very strong magnetic particle. It's a single domain. It will always be magnetized in one direction. But the gold with chiral molecule is a weak magnetic particle. So it depends on the current. You can have a magnetization or non-magnetization of the gold. So this is how the device looks like in real space. This is the two contacts. This is the magnetic particle sitting on top. And we have chiral molecules which you don't see it. And here you have the two-level memristor-like behavior. You will have either high resistance, low resistance states, or low resistance, high current state, and you can switch between the two by changing the voltage. So this is a 30 nanometer device, which we can done by the CISS effect. So far, I hope I have convinced you that we can have a very small device. It's 30 nanometer in size. It could be very efficient, very simple to do, and it could have a very standard technology or standard lithography that could be done by that. And this is the memoristic behavior that we get from this 30 nanometer device. But if we want to go to industrial this kind of effect, we should think about not using organic layers as the chiral molecules that we took from biology. We use polyalanine, which are organic molecule. We can talk about chiral oxide. Can we switch the chiral layer of the organic molecule by putting an oxide here? And this is done by aluminum ALD, atomic layer deposition. And then we have again a bottom and a top contact, and a ferromagnetic layer, which we magnetize as up or down and see the resistance changes. And this is a multi-layer process of device. We take a silicon chip, we photoresist, then we evaporate by ALD, evaporate the gold contacts, then we put by ALD the chiral oxide, we put a ferromagnetic layer and a top contact, and by doing those, we can have this kind of devices. And if we check the spin polarization is defined by the current where in one direction of magnetization minus the current in the opposite direction of magnetization, because here we inject one spin, here we inject the opposite spin, divided by the sum, and we get almost 100% spin polarization. If we switch the chirality of the layer, we should have the opposite effect, the opposite spin polarization, and this is exactly what we see. Here the up magnetization shows the high current, and the low at the bottom, the minus magnetization is showing the low current, and we have again 100% spin polarization. So this device could even work under the conditions of very high, under the conditions of other left or right chiral oxide. So not only it is simple, you can really do it in standard integrated circuit technology. Of course, we can do multiple layer and have like two polarization and have L and D together. And of course, then we don't see the effect of the magnetization. And we see similar for both up and down, similar effect for both up and down magnetization. Can we have an optical memory? Yes. So this is a result of an optical memory. Here you can have a nanodots sitting on a ferromagnetic substrate. And wherever we put light, we act. We have spin transfer, so we magnetize the layer, and we measure the magnetization by measuring a Hall sensor. We drive current here, measure voltage here, and this voltage is sensitive to the local magnetization. So using chiral layer, we have a magnetization. We see a Hall signal wherever we shine light. Wherever we take the light off, the Hall signal dies. If we take a non-chiral layer, which are similar molecules but non-chiral, we don't see the magnetization. So we can have not only that it is simple, we can have both optical and magnetic-like memory devices using this kind of effect. We can go even smaller, and we can go to 10 nanometer size particle, and this is taking magnetic particles which are not stable at room temperature, but with the chiral magnetic layer, they become stable, and this is very close again to the thermodynamic limit. And with chiral molecule, we see this hysteresis loop at room temperature, and this is like a ferromagnet. Without the chiral molecules, they are not stable, they are becoming paramagnet. But if we want a memory, we want the magnetization to be stable in one direction, and this is indeed the case if we use chiral molecules. So in principle, using this effect, we can go even to 10 nanometer memory, magnetic memory, using this kind of an effect. What about using more sophisticated material like magnetic impurities or antiferromagnetic material? The answer, we can use those as well. And this is by using the chiral layer and using what we call exchange interaction. So this is a chiral molecule which is getting closer to a magnetic substrate. Since we have charge redistribution, it's behaving like a small magnet, and this small magnet interacts with a magnetic substrate. So you can have the same opposite spins, which we call with the Pauli principle. This is a strong interaction. This is like when you put two magnets, one close to the other with the opposite polarization, you will have strong interaction. And this is a high spin, we will have a large exchange interaction or large or weaker interaction because we are in the same direction. So they are much farther away. The distance in energy between those two is hundreds of milli-electron volts, exactly what the energy that we were looking like. We published this paper in Science because this could separate between enantiomers, and I didn't tell you that in chemistry, if you do drugs or synthesize, we want to separate because one drug with one chirality is good for biology, while the opposite is not. But we can even use this for a device. We can use this for a device. What we do is we take ferromagnetic substrate, we put chiral molecules on top, and observe the chiral molecules on top of this device. And if the chiral molecules are adsorbed on top, so this is chiral molecules so sitting on a ferromagnetic substrate, and then we ask ourselves, do we influence the magnetization? Can we have very local memory devices using those chiral molecules? So this is a chiral molecules. This is a L, one kind of chirality, and the opposite kind of chirality sitting on a magnetic substrate. So we can have either up magnetization or down magnetization using those. So if you put L, we'll have magnetized up. So we force the magnetic memory to be up because it interacts with a small magnet of the chiral molecule. Or if we have the opposite chirality, we have a down magnetization. This is measuring the magnetization because it forces flips the magnetization of the substrate. So this is done by magnetic force microscopy, and this is done by atomic force microscopy. We map where the molecules are and force the magnetization. Is this efficient? It's one of the most efficient processes in magnetization, because if we told you the spintronics is not efficient, here we can use 12 orders of magnitude less electrons than standard spintron transfer or the standard spintronic devices. So it's becoming a very, very efficient way to induce magnetization, and even without these very, very small currents going. So not only that we can do small memory devices, we can do optical and electrical memory devices, we can use chiral oxides, we can also use very small currents, so we can be very efficient. So the magnetization is metastable, it's enough. So, but what is the energy scale of this magnetization? This could be measured directly with atomic force microscopy. So we can ask ourselves, let's take atomic force microscope, put a spacer and a chiral molecule at the end, and ask ourselves what will be the related energy to this kind of interaction, because we can switch the magnetization and see the energy difference if we pull the forces out. If it's 6 times the orders of the room temperature, which is around 150 milli-electron volts, this means we'll have a very stable magnetic memory at room temperature, but we'll have also a way to induce this magnetization in a very simple way. So we expect, again, that if we put the opposite, the same chirality, and the magnetization will be in the same direction, this magnet and this magnet will be in the same direction, we'll have high spin, and this interaction will be weaker than opposite magnetization, where we'll have something like two spins which are opposite each other. So this is like an S bond, or it's a Pauli principle, but those electrons could be very close to adjacent to each other. So this is an experiment. This is a CISS on the AFM tip, and those are the measurements. With chiral molecules, we see large forces. Without chiral molecules, we see weak forces, and we don't see difference in magnetization. And if we want to compare the down and up magnetization in energy, what we could do is measure the difference in energy in exactly 150 milli-electron volt, the energy which we expect to have as a difference between those two, or this is what we want to have when we have spintronics-like devices. So the energy scale is exactly what we want to do, and it's a very simple way to have a memory-like devices. It could be used, the same kind of mapping could be used to have very local mapping of magnetic field or magnetic surfaces, because we don't need to have the tip to have very far, like magnetic force microscopy is working. What we'll have, what we have is a mapping that we can have very local mapping of this kind of effect, and this mapping could be very, very local. So I see I have to finish now because my time is almost up. So I want to say you that we can induce magnetization in a very, very in many different ways. And we can talk about skyrmions. We can have, when we have magnetic memory devices, we'll have or magnetic defect. We can talk to those magnetic defects and have very dense memory devices, or use antiferromagnetic material to have to talk with those and have even denser memory devices. To what is our future idea? We can use paramagnets, we can use ferromagnets. Paramagnets is magnetizing or have a gradient of magnetic field. We can use ferromagnet and antiferromagnet to have very efficient spintronic devices. So with that, I like to summarize and I tell you that the CISS effect is important for biology, physics, and chemistry. I didn't talk about the importance for biology and chemistry, only by a brief points, but I'll show that you can have very efficient spintronic devices using this kind of effect. And thank you for your attention.